About test number 2, it's touchscreen today. Test 2 is on Thursday, okay? So next Thursday. So I would like to be done. Yeah, I should be done today. So for test 2, remember when we talk about equipotential? And equipotential, they are like contour line, okay? So that means at that point, you're going to have the same potential than here, there, okay? So at that point here in space, you're going to have potential. So the potential is, by definition, the energy, so the potential energy for 1 Coulomb, okay? So potential, it's energy per 1 Coulomb, but it's always relative to some reference level. So when we, for example, we compute the potential generated by a point charge, right? It's relative to infinity. So we suppose that very far away, there is no energy. Okay, so it's always property of 2 points. My point is, don't forget the following. So when you have equipotential, so we did that, I'm not going to do that again, but let's say you have equipotential, it looks like contour line. And the electric field, so the electric field is a vector. Okay, so the electric field is, by definition, the slope of the equipotential. So when those equipotential are very close to each other, that means the slope is the largest. So by definition, the electric field, okay, is the slope. But it's actually touchscreen.
Oh, it's touchscreen? Oh.
It's actually the gradient. So by definition, the electric field is the greatest slope. So if I ask you, for example, is the electric field the strongest here or there? It's going to be at point B because the slope is the largest, right? So you see here you have a larger slope than here because you have to think of contour line. And the electric field will point to the direction where the potential is falling. Okay, so the electric field is showing you which way to go to lower the potential. So remember that the electric field is the slope, but in 2D or in 3D, it's a gradient. So it's the largest slope. Okay, so if you see contour line, that's where the largest electric field will be. Okay, so it's just a review. It's a question on test 2. And then another thing, okay, another thing that you have to remember, I don't know if it's for the test or the pop quiz, but I told you that, let's say you have an electric field in space, okay, so these are the electric field lines, okay, so it could be the electric field produced by a fish, and if you place inside its touchscreen a non-conducting material. Okay, so this is non-conducting material. It can be polarized. Okay, so it's like made of molecules. So this you're gonna have minus, 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 plus, 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 minus, plus, minus, plus, minus, plus, minus, plus. So if you have an electric field and you have a non-conducting material inside, like a dielectrics, that you place between the plates of a parallel capacitor, you see here you're going to have plus, 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 minus, minus, minus. So the electric field inside will go this way. So if you have a conducting material inside an electric field, it will make the electric field weaker. So it's the story of the fish, right? So if you have something that is not good to it, the electric field will get weaker. Now, if you have a conducting material, it's going to be the opposite. So let's say you have an electric field and produced by that fish, and now you have something that is good to it. So in that case, the electrons, they are free. Okay, they can move freely. So all the electrons are going to go this way. What will be left here? It's going to be plus, plus, plus. So it's going to make its own electric field. Minus, minus, minus. Go in, go in, go in. plus, 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 go out, go out, go out, go out. So it will make the electric field stronger. Okay, so remember, non-conducting material like a dielectrics inside an electric field, it will weaken the electric field. If you have a conducting material inside an electric field, it will make it stronger. It's touchscreen. Okay, good. Okay, so it's for the test or the pop quiz, I forgot, or maybe both. Okay, so we were doing parallel circuit. So if you have 24, 24, 24 in parallel, so the equivalent resistance will be 24 divided by 3, which is 8 ohms. Do you agree? So if you have something like this, right? So first of all, we're going to take care of the parallel. So do you want to do it? So you have boom, 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 2 lanes, and then it's combined again, back to base. A touch screen today. So you have 12 to the minus 1 plus 12 to the minus 1. Okay, and then to the minus 1. So the equivalent resistance here is 4. It's in series with 8, so you just plus 8. That will be the equivalent resistance. Agree? Okay, so it's just a review. And if you want to use the engineering way to solve the circuit, you start with the power supply. So it's when you have what it's called complex circuit, but it's not that complex. Complex circuit is really when you have more power supply. So in that case, it's easy. You go boom, 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 boom. Nothing happens. Ooh, I have 2 lanes. So you make 2 lanes here, 6 ohm, and then you have a 12 ohms. Okay, boom, boom, boom. Combine again. Okay, and you have 8 ohm. Okay, so you have a voltage drop here and a voltage drop there. Right, so we did that last time. So you're going to have the current drain from the power supply. You're going to have I1 and then I2, and then it combines again. Okay, so that's for the methodology. And you will solve it step by step. Okay, you will replace this part by 4, this part by 8, and then you do 8 plus 4. Okay, so at the end, it's going to be 1.5. Boom, 12, current I. You can solve for I. Are we good? Okay, I'm not good. I'm gonna do another one, but we did one like this. Any question? Are we good? This one is in parallel, so I'm skipping a step. It's because like if I want to do the whole thing, I should do here 1.5. Boom. This part here is equivalent to a 4 ohm. Okay. And this part here is equivalent to 8 ohms. And then this is equivalent to 1.5. And then boom, 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 12. Okay, so the current here, it's going to be 1.5 divided by 12. Agree? That's easy, right? So 1.5, 0.125. Agree? Okay, so the only thing that is sometimes hard, I mean, sometimes you have to remember this is the same altitude here. They have the same altitude. So here you're gonna have a drop, a voltage drop. So that will be the voltage across that resistance here. So it's gonna be 0.125 times 4. Is it 0.125? Wait. Do you agree? Are you with me? Okay, so 0.5 volt, and that will be, obviously, it's going to left 1. Okay, either you do 1.5 minus 0.5 or you do 8 times 0.125. So from here, you're going to step one step back. So that's going to be 1 volt. This is 0.5 volt. So for example, you can find I1. It's the voltage drop over the resistance. I2 will be half of I1. Okay, so just a reminder. So if you do it this way, it's easy. Okay, let's do that quickly. What is the equivalent resistance? It's touch screen. Don't stare. Do it, do it, do it, do it, do it, do it. Not you. Them. So 3 and 3 in parallel is going to be what? 3 and 3 in parallel is going to be? Yeah, 1.5 because it's the same. You divide by 2. Okay, 1.5. You drop it. This one, drop it. Okay, this one, 3 and 3 and 3 and 3 in parallel. What? Okay, and then you combine 3, 4, 5. Boom, 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 boom. 5.5 ohms. Agree? So they are just asking you to find the equivalent resistance. Agree? Okay. About you awake, be awake. About test number 2 again. Let me show you like the type of circuit you might have. It's touch screen. Touch. Okay, so let's say you have a parallel circuit here. So you have a 2 ohm. And boom, boom, boom. This one is from the practice test. Chi. Boom, boom, boom. Power supply 8 volt. And they are only asking you to find the voltage drop, let's say, across this one. Question mark. So usually you have a A and B. Okay, so this is plus, this is minus. So the voltage at A is larger than B. And they want you to find VAB. Because that by convention, this is VA minus VB. Voltage is a property of 2 points. So here you don't have to solve the whole thing. You don't need to solve for the equivalent resistance. So first of all, you can start with this. Okay, you have 2 branches. This is 2. This is 4. Okay, and then here you have, it's like 2 pipes, right? You have 3. And then here you have 9. And you come back to base. You're gonna see I don't need to go all the way. It's touch screen. So the 4 and 2, it's gonna be what? 6. So this is 6 ohms. And then 9 and 3, it's gonna be 12 ohms. And they are in parallel. But they are not asking me to find the equivalent resistance. I can take a step further, but because I don't have anything here, I can actually stop here. Because look, what's going to happen is that here, what's the voltage drop here? Between here and there. Think of altitude. This is 8 and this is 0. So what's going to be the voltage drop? Huh? The voltage drop. You start from an altitude 8 yards and here it's 0. It's between 8 and 0. What's the voltage drop? 8. You have to think as a hill, it's a mountain. You start from 8. A voltage is like altitude. Voltage is to electrostatics what altitude is to gravity. Okay, so it's like you start from 8, you go to base. Base is 0, so the voltage drop is 8. And I can stop here. I don't need to go further because I want to find the current here. They have the same voltage because they are in parallel, because they drop by the same altitude. They don't have the same current, but they have the same voltage. Okay? So then, because my goal, remember, my goal is to find here the voltage drop here. So first I'm going to find the current. Can I find the current now? Yes. So I1, it's going to be the voltage drop divided by 6, isn't it? So 1.33 repeating. So I2, it's going to be, I don't need this one, but I can pretend that I need it. So it's 0.6 amps, right? I can even find I now, you see, because 1.3333 plus 0.6666 is going to be 2. So it's like water flowing. Some of it will go through here, some of it will go there. This one is a wider, it's like a wider pipe. So you're going to have twice as much as here because here you have more resistance, so it's like tighter. So once I have that, okay, now I have I1, okay, which is touch screen. Yes, 1.333, and I have here 0.6 amp. So can we find the voltage drop now? Yeah. You see, you have 2 voltage drop. Exactly. So it's going to be 1.333 times 2. So you have to think, if you want to go fast, you have to think as altitude, like measuring tape. You are losing altitude each time you pass a load. Each time you pass a load and you go from plus to minus, you go toward the ground, you are losing voltage. There is a voltage drop each time the current goes through a load. Okay, it's going to be important for what comes next. Okay, if the current is going this way, that means this is high altitude, this is lower altitude, so you are losing, it's a drop. Going this way, when you go with the current, you are losing altitude. If you go in the opposite direction, you are gaining voltage. So if you are inside the power supply, okay, that's going to be important for next. So let's say you have a 1.5 volt. This is plus, this is minus. When you go this way, you gain. Okay, going that way. If you go that way, you lose. So if you go with the current, who load, you are losing. And how much loss do you have here? So it's going to be 1.33 times 2. 2.66. Exactly, 2.6666 repeating. And the other one will be 8 minus 2.666666 repeating. Which is 5.3 repeating. So 2.6 repeating plus 5.3 repeating is 8. Agree? Because the question was find that voltage drop. So you're gonna have something like this for the final. And of course you can keep going. So if you were to keep going, I can do 8 volt. Okay, and then I have everything happens like you have a big resistance here, which is 6 to the minus 1 plus 12 to the minus 1 to the minus 1, which is 4 ohms. Okay, and 8 divided by 4, that will be 2 amps. So the equivalent resistance is 4 ohms. Okay? Before we move, I just wanted to show you a picture. So it's just a picture. So this is a picture of, you see, a circuit with a battery. And we talked about internal resistance. And this is a nice schematic because you see what's going on. Everything happens like you can replace your battery with two components. One is the internal resistance that gets larger as it gets older. And here it's called the EMF. Okay, so the terminal voltage is across the battery between plus and minus. And here you have the load. Larger is the current, more voltage you're going to lose to the internal resistance. Larger the current, Ohm's law, larger the voltage drop. Yes. Okay. So this is what they called R2R network. We have seen that last time. And you see, the idea is to go from digital to analog. And you need like a op amp. So it's called digital analog converter R to R. So just show you how it's used, right? So you do 0, 1, 0, 0, and then you're gonna have an analog value. For those going into electronics, what did I want to show you? Okay, so this is household wiring. It's from the website Hyperphysics. Hyperphysics, right? So here you have a transformer. You're going to go from 4000 volt to 120 volt, and you have two hot wires. So one will be 120 volt, the other one is 120 volt, but they are out of phase. So in between them, it's going to be 240 volt. Okay, so if you have like a washing machine, 120 out of phase, that will be 240 volts. And then you need to have something connected to ground. So the return path goes to ground. Although you cannot trust the return path because sometimes you still have some voltage drop. So you can be electrocuted or shocked. But the ground you can trust because the ground goes to ground for sure. Did you hear our French president? For sure, for sure. It's making the buzz everywhere, for sure. Okay. Okay, so here you have another picture. See, 4000 volt goes to 120, 120, two hot wires. This is the neutral path. And here you can have your washing machine that will be 240 volts. Between here and there, you have the other appliances. Somewhere you're going to have fuse breaker to make sure that you don't go over 20 amps. For sure. Okay, so now you should be able to solve those type of circuit, right? So you do 5 and 10, that will be what? 15, 20 and 10, that will be 30. And so you have 15 and 30 in parallel, right? If you have something like this, so you have two components in parallel with each other. If I close those switches, so if I don't close the switch, what's going to be the equivalent resistance? If I don't close the switch, this is open, this is open. What's going to be the equivalent resistance? Here it's going to be 10, but here I have 20, so it's going to be 30, right? So how much current do I drain? 9 divided by 30. But if I close it, and I close this one and I close that one, what's going to be the equivalent resistance? So it's 10 and 10 and 10. Yeah, in parallel 3.33, right? Plus 20, that will be 23.33. So I'm going to drain more current when I have a parallel circuit. So you drain more current if you close this one and close that one, because it will lower the equivalent resistance of this part. Okay, and about the pop quiz also for today. So, yes. Can you go back to the first survey you showed? The one before the last one. Oh, I closed the thing. This one? No, the one. This one? Yeah, I don't understand. Can you explain the? So you go from here, boom, 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 and then it goes in two branches. So it's two branches in parallel. But in these branches, it's gonna be in series. So it's gonna be 5 plus 10 is 15. Okay. And the other one's 30. And the other one is 30. So you go from 20, boom, boom, boom. Ooh, intersection here. And then you have two lane. One, it's continuous here. Okay, so one will be 10 and 20. And this one is also continuous. There is no intersection. So 5 and 10 combined together. So it's going to be 20. This one is boom, 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 30. And this one is 15. And then that will be in parallel. Okay? And what else? Oh yeah, just one more thing for we have to finish today. One more thing about the pop quiz. If you buy a light bulb, right? Used to be incandescent light bulb, you're gonna connect that to the outlet. The outlet is 120 volts, and you buy, let's say you buy 40 watts light bulb, and then you buy also a 100 watt light bulb. So that's gonna be for the pop quiz, and you connect that to an outlet 120 volts. This is called the RMS, root mean square. So anyway, that's what you measure with the voltmeter. So you see that they are both using the same power supply. So the resistance, so you can say the power, so how much energy is being consumed is just V squared over R. Okay, I can use that equation. So that will be 120 squared over R, which is 40 watt. In that case, the power will be 120 squared over R2, this is R1, equals 100 watt. So which one has the largest R? Which one has the largest one? The largest R? The first one, right? Yeah. So of course R1, okay, will be larger than R2 if the wattage is less. To make sense, because if you have more resistance, it will make harder for the current to flow, and that's what you want. It's not going to be as bright. Okay, so this one will be brighter, it's going to consume energy quicker, higher metabolism. Do you agree? But so that's good. However, if you place them in series, what's going to happen? That's something we never do. So if now we have that 40 watt in series with 100 watt. So this one has a larger resistance. And you plug that in the outlet, 120 volts. And the current is the same because it's a circuit in series. Which one will you think will get the largest voltage because of Ohm's law? So Ohm's law, okay, you have voltage V1, voltage V2. The current is the same. Which one will be the largest voltage drop? V1 or V2? V1 will be larger. Do you understand? Because the voltage drop, okay, is the resistance times the current. The largest resistance in a circuit in series is taking all the voltage drop. So which one will be brighter? The 40 watts, which is you don't want that, but that's what happens in a circuit in a series. So this is a no-no. You never do that in a household. You don't do that. Instead, you're gonna use parallel circuit because each one of them will get the power they need according to their resistance. Okay, so if you have appliances in series, one of them will not work, and one of them will take everything from the others. Okay, so that's gonna be for the pop quiz. Kirchhoff law for current. I think Kirchhoff has nothing to do with that rule, but it makes sense. Whatever comes in has to come out. So if you have an intersection, you have 7 amps in, it has to add up for whatever is coming out because there is no leakage. Okay, it doesn't leak. Okay. Okay, so this is called Kirchhoff law for voltage, but it's just the definition of voltage. So if you have a circuit in a closed circuit, okay, the sum of all the voltage will be equals to 0 because the electric field is a conservative force. So even inside the circuit, you're going to have an electric field. You go around and the voltage difference will be 0. So what does it mean? It means you start from here, you lose, you go from plus to minus. So you are losing 10 volts, yes? And then you are losing 2 volts, yes? And then you keep going around, you go with the circuit. So from minus to plus, what's going to happen? You gain 12 volts. Okay, so it means that the sum of all the voltage, if you go into a loop, it's going to be 0. Okay, because it has to do with the electric field. So if you are in a circuit like this, the sum of the voltage will be equals to 0, the voltage drop. Okay, because here you have an electric field this way, and you have an electric field this way, and you have an electric field that way, opposite. Okay, so for example here, let's try to do this one and then you will understand Kirchhoff. I hope I say it right. So the current is going this way, yes? So as you go through a load, you're gonna lose the voltage or you are gaining voltage. This is water flowing. Water flowing goes from a high altitude to a low altitude. So do you agree that you are losing voltage? Yes? If you go this way, so I'm gonna do 12 times I. You are losing. Boom, 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 boom. Plus, minus. You are losing if you go this way, or you are gaining. From plus to minus. From plus to minus. From high altitude to low altitude. From the plus to the minus. You are losing. Okay. Keep going. If you go with the current, okay, you are always losing because it's like water. Water goes from high to low. So you are losing. Do you agree? Okay, so minus 8I. And now from here to there, because you have to follow the current, right? So now you go from minus to plus. You are losing or gaining? Gaining. Equals 0. Okay, so if you go along a loop, okay, you follow the current, the sum of the voltage drop will be equals to 0. Okay, this is only true if there is no electromagnetism involved. Okay, so then you can say, what can you say? You can say 12 and 8, that's minus 20I, minus 6 plus 24 equals 0, and you can solve for the current. Agree? Yeah? So this is called Kirchhoff law for current. And you find current equals 0.9 amps. Why do we bother doing this? Because we can have this type of circuit. And you see, you have a power supply here and you have to power supply there. So I'm not going to do it in details because you have to use your TI and you need to solve a system of equations. But the question is find the current IA that is flowing through that branch, find IB, and find IH. Okay, so you could have a situation like this in your car because you have the alternator and you have the battery. So sometimes the juice will go from the alternator to the battery when it's charging, but when you start the car, it's the opposite, right? It's the battery producing the juice, so the current will flow from here to there. So you never know what really is going on. So how do we solve those problems? We have to use Kirchhoff law for current, Kirchhoff law for voltage. So the first step, but you have more advanced way. This is the longest way, but you learn if you take a class in circuit how to do it. So first of all, you decide totally random. You decide which way the current is going. You don't know. If you find a negative value, it means it's opposite. It's going in the opposite direction. So you decide arbitrary. Okay, so I decide this is this way and this is that way. Are you with me? So I show you because it's one assignment problem. I'm not going to solve it because then you have to use your TR. And I have a YouTube, and I'm sure in Dropbox, I'm sure in Dropbox you will find a video, or you have a YouTube, you know, how to solve a system of equations with your TI. So the first equation is easy. Whatever comes in has to comes out. So IA plus IH, IB, sorry, equals IH. Agree? Yes? Okay. And then I'm going to go around here. I'm going to go this way. I'm going to go this way because IA is going that way. So you have IA, IA. Agree? I'm going to go around and I know that the sum of all the voltage drop has to be equals to 0. Okay, so let's start from here. You go 14 volts and the current is going this way because it goes from the plus. So from minus to plus, do you drop or do you rise? You rise, very good. So it's going to be 14. And then you see here, because you're going from with the current only is going down hill. So it's a drop. Do you agree? Okay, current is like water. So it's going to be minus 0.1 IA. Boom, 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 boom. Oh, look at that. I'm going uphill like a salmon. So it's not a drop anymore. I'm going uphill. Okay, the current always goes from plus to minus for a load. So now it's going to be plus 0.01 IB. And then from plus to minus, it's going to be a drop. Plus 12 equals 0. That's my second equation. And then I do the same thing. So I have to be faithful to my current. So current is going this way. So it means it's going this way. This way, sorry. I have to be careful. So this is IH, this is IH, and now here it's water flowing. I have IB. This is IB. Agree? Because in the branch, there's the same current flowing. So from minus to plus, is it a drop or a rise, right? So plus 12. And then from here to there, it's touch screen. Is it a drop or a fall? A drop. A gain or a drop? It's a drop. So 101 IB. And then boom, 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 boom. And that's a drop also, right? So minus 1.2 IH. Okay, so now you have three equations with three unknowns. You have to be careful, but I can make mistake. 14 is a plus, right? Huh? This one, which one? This one? No. This one? So this one, it was, I'm lost. Okay, so this one, 14 minus da 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 da, and then here it's a plus da 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 da, and that's a minus. Thank you, because you go from plus to minus. Is that right now? Okay, and then you can do the matrix thing, and you do it the way you want. IA, that was IH. Or IH, or IB, IH. So IH here, I have minus 0.1. IB, I have 0.01. IH is 0. And the last column will be 12. So it should be part of the same matrix, right? See, I forgot my linear algebra. But you know how to do it, right? IA, IB, IH, and here you have 12, and so forth and so on. IA 1, minus 1, 1, 0, and here it's IA 0, IB is that minus 0.01, minus 1.2, minus 12. Okay, you double check because this is not physics anymore. You don't have to do the matrix way, but that's how to do it. Okay, I have it here. I just wanted to show you how to do it, and then you can use your TI. And then there is a Dropbox video. Any question? You survive? It's a matrix. You have different way to solve the matrix. Oh, and look, there is a textbook. Okay, no question. Good. Okay, so very quickly, AC. So the circuits with the batteries are DC, direct current. In reality, from the outlet, you have AC, alternating current, right? So somewhere you're going to have a power plant. You have a turbine that will spin. It will spin at a rate of 60 turns per second. So here you're going to have an alternating voltage and an alternating current. Okay, from the outlet. Okay, so this alternating current here is going to follow a sine wave. So I can show you. I have an R. Okay, this is my outlet. It doesn't go to 60 hertz, but in reality it's 60 hertz. You have your light bulb. We're going to connect the 120 volt. And I'm not going to ask you to solve multiple equations. for the test because it will take too long, but it's in the assignment. So if I take an oscilloscope, right? So that will be the oscilloscope, and I connect here. So that will be the voltage across, and you see that the voltage is following a sine wave. Okay, so the sine wave has a period. So the period will be the time between two crests, for example. So if I look at the value, you see the frequency is 0.5 hertz. So 0.5 cycles per second. So one cycle is how many seconds? 0.5 cycles per second. Wake up, you are doing something else. 0.5 cycles per second. How many seconds per cycle? 2. 2, huh? 1 over 1/2 is 2. So you see from crest to crest, okay, that will be the period. The frequency is 1 over the period. Now, not only the voltage is AC, but alternating, but the current, right? The current is also AC. So it's also following a sine wave. And why do they use a sine wave? Because when you have a circuit, sometimes it's like taking the derivatives, taking the integral, adding signal, subtracting signal, multiplying signal. And when you deal with sine wave, it's easy because if you multiply sine wave, you get a sine wave. If you take the derivative, you get a sine wave. If you take the integral, you get a sine wave, a sine, and so forth and so on. So we use sine wave. Agree? So that's how it works. So that means relative to the ground, the hot line will go from plus 0 minus plus 0 minus. So it means, you see, the hot line will go from 0, maximum is 170 volt, the maximum. And then here minus 170 volt and 170 volt, minus 170 volt. But I'm not going to explain, but you do have a video that will explain it in Dropbox. If you take your voltmeter like I did here, you're going to measure what we call the RMS. And this will be 120 volt. Okay, so in AC, from the outlet, okay, so the voltage follows a sine wave. That's going to be 170 volt. But when you use a voltmeter, okay, you're going to get a value which is 120 volt. Put mean square, and that will be equals to the 170 divided by square root of 2. So any alternating current, you can measure the RMS, which is the max of your sine wave divided by square root of 2. And that's the way it is. Yes. Okay. Any question? Looks like this. Okay, this is good. You see plus, and then it gets to minus, plus to minus. So the hot wire goes to 170, 0, minus 170, 170, 0, minus 170. Okay, so it goes back and forth, back and forth. That's the only way we can do it because it's because of induction. Oh, by the way, but you don't share because you are here. Not everyone is here. So you see here, I have a hat, and on my hat you have the Maxwell equations. So someone asked me, that's why. And some of them, you have 4 Maxwell equations. Those Maxwell equations, they unify magnetism, electrostatics, and the way we make AC, which is called electromagnetic induction. Okay, so it's amazing. It was the second unification in physics for equations to predict everything in magnetism, electrostatics, electromagnetism, and it even predict electromagnetic wave. So for the final, if you show up but don't share with something like this, with the 4 equation of Maxwell's on a t-shirt, on a hat, or something like this, and it has to be because you have 2 forms, right? So this format is the integral format. Or you can do the other format, which is vector calculus with delta. But if you have that somewhere on you, I'll give you extra credit when you're gonna give me your final, okay? But don't share because you are here, right? I say it once, I'm not going to say it twice. Okay, that's for extra credit. Maxwell equations. We will do that next unit. Okay, so alternating current, you see, you can visualize it this way. Okay, equation, just a little bit of math. You can try that with Wolfram alpha. When you have a sine wave, okay, it's always the same equation. It will be here, you're going to have the max. So in our case, it's going to be 170 volt. And in the US, the frequency is 60 hertz. Okay, so in the US, the maximum here is 170 sine. So you always have 2 pi, always. And you always have the frequency here, which in our case is 60, and here you always have the time. So this is the general equation for a sine wave. F is the frequency, unit is hertz, and it means the number of cycles per second. T, it's called a period. The unit is in second, and it's the opposite. So it's a reciprocal, number of seconds per cycle. So we have frequency equals 1 over t. So for our outlet, maximum is 170 sine 120 pi t. Okay, so it's a function of t. Okay, the period is 1 over 60 in seconds. In the US, which is like I don't know, 0.07 second. In Europe and everywhere else on the planet, it's going to be 50 hertz. And the RMS, when you use a voltmeter, is 120 volt. But if you go to Europe, it's going to be 220 volt. Blame Edison. Okay, so that's in a nutshell. Okay, now if you use the RMS, so again, what's the RMS? You take the maximum value and you divide by square root of 2. Same thing for the current. So if you use the RMS value, then you can use Ohm's law. So it means even like, for example, if you have an audio system, so if I have my laptop, I have to turn AC to DC. That's what is going on in that charger, because my laptop cannot take AC, can only take DC. So it's converting 120 volt to 20 volt. But if you have an audio system, no, you don't want DC, you want AC. You want something to move with time because sound waves. So in that case, okay, even though you have AC, you can apply Ohm's law only if you're using the RMS. Agree? It's just nothing to understand. It's just I'm telling you. That's the way it is. So the RMS, okay, is the peak value or the maximum value divided by square root of 2. So for example, in that case, you step down 120 to 30 volt or 34 volt. So the RMS will be 34 divided by square root of 2. Agree? And then you just use Ohm's law. V RMS equals I RMS times the current. So it's going to be 34 divided by 8 amps. So in the AC circuit, okay, you can apply Ohm's law only if you are using the RMS values. And the explanation is interesting. It's in Dropbox. You can, there's a video which is called RMS value. Okay. Okay. And you can find also the power consumed. You use also the RMS value. Question? Okay, blah 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 blah. Done. Okay, so a few more things about charging and discharging the capacitor, because it could be important if you go to electronics. So a lot of application for capacitors. First of all, you can use them as a what? High pass, low pass filter. Low pass filter, which means that you're gonna remove the noise. Okay, so you can use the capacitor for that. You can use that for the pacemaker because it will be like a way to store energy and to burp it out after that. And maybe you have done that in the lab, right? You can charge and discharge a capacitor. So if you have a power supply, which is a square function, on, off, okay, and you have the setup here, the capacitor, which is in series with a resistor, is going to charge and then discharge and then charge and then discharge. Sometimes it doesn't have the time to charge completely, so you're going to get something like this. Okay? So this is not on the final, but just I wanted to show you quickly how it works. I have a very nice simulation here. Okay, so you have a capacitor. Agree? You have the power supply and you have a load. Okay, I'm gonna charge the capacitor. So I'm charging the capacitor. So you see, at the beginning, it goes very quickly because it's very easy to have positive charges here. To remove the electrons, you have positive here, negative there. So the battery is doing work, okay, to place those charges on those plates. After a while, the capacitor is charged. Do you see any current flowing? Is there any current flowing in the circuit? No. You can open it, okay? And the capacitor is fully charged. Okay, so it's storing charges. You can use it, okay, maybe to make a memory, for example, random memory in your computer, that will be a 1. It's charged and it's going to hold the charge. The voltage across will be exactly the same voltage as the power supply. And then you can discharge it. So I'm going to close here. It's going to discharge into the load. So that will be your heart. Now it's going to discharge and you have an exponential decay. So that's how it works. So first it's going to discharge very quickly like a phone, 100% very quickly. It gets to 80% and it takes forever to get to 0. Okay, I have another something here. So you have a battery, you have the capacitor, and you have the load. So first you're going to charge the capacitor. So I'm charging. So first the current is very large, right? And then the current is going to decrease with time because now the capacitor is stopping any current flowing. Okay, the voltage across the capacitor equals to the voltage across the battery. There is no more current flowing. it's behaving like your open switch. It's like an open switch now, and it can hold the charge. And now I'm going to discharge it in the load. So first the current is very large again, and then it's going to decrease, 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 and there is no more current. Okay? So you can imagine, this is the math here. There is an equation. I will show you the equation. But when you are charging a capacitor, it's very much like you have a reservoir here, empty reservoir, and you have a pump. So that will be your battery, and you are pushing the water in. Is it going to be easier at the beginning, or is it going to be easier at the end? At the beginning, it's going to be easier, right? Because there is no water to push against. So first, the capacitor is going to charge very quickly. You see, this is the slope, very quickly. And then the battery has to do work. Because you already have so many pluses, and you need to add another plus, and then another plus, and then another plus. So it's going to get forever to fill your capacitor. Does it make sense? Now we can define a physical quantity called the time constant, and it means how long it's going to take to fill the capacitor by 63%. So that will be the time constant. Of course, it's going to depend on the capacitance. If you have a big reservoir, it's going to take longer. It also depends on the resistance you are charging through, because it's like a pipe. Okay, if you have a small pipe, it will take forever. If you have a larger pipe, it's going to be quicker. Okay, so this is called charging the capacitor. Are you paying attention? Because otherwise I'm going to add that to the test if you're not paying attention. So that will be the equation for the voltage across the capacitor. So a capacitor is resisting the building up of the voltage, right? You have a beautiful equation here. Everything is in equation. Okay. And then I'm skipping the math, but then you have a discharge here. So that is called discharging the capacitor. So at the beginning, it's going to be very quick because all the water here is pushing, wants to go down, and then it takes forever. This is called an exponential decay. Are you with me? Okay. For those going into circuit electronics, engineering electronics, in Dropbox, I I have a video explaining charging and discharging. Okay, I made a video for you if you are going into this field. But here I have, see, charging. Oh, this is just charging. Okay, you can watch my videos. Okay. So you should watch the video. Maybe for the pop quiz you need to remember that at t equals 0. So let's say you have a circuit, right? You have your power supply, you have your resistance R, and you have your capacitor. So at t equals 0, the voltage across here will be equals to 0. Okay, because you didn't put the first charge yet. Okay, so at t equals 0, you can replace your capacitor just by a wire. It's like it's not there, and the current will be maximum. Okay, so it starts to charge. Okay, starts to charge the plus and the minus, and the current is going to be maximum. Okay, because the capacitor didn't stop the current yet. So at t equals 0, the capacitor, you can replace it by a wire. So it's going to charge, And when it's totally charged, you can replace the capacitor by an open switch. And the current will be equals to 0. Okay? And the voltage across the capacitor will be equals to the voltage of the battery. And here, the voltage across the capacitor equals to 0. Okay. Any question? Went a little bit fast. But here you can see that at the beginning, you're going to have a lot of current. The capacitor is not stopping the current. And when you wait long enough, there is no more current flowing. Okay, if there is no more current, there is no voltage drop across the load, and the capacitor is holding the charge, and the voltage across the capacitor will be equal to the voltage across the battery. When you discharge, so the switch is here. When you discharge, I close the switch there. The current is going to be very large. See, the motor is going to work. And then little by little, the current is going to decrease. And now the capacitor is behaving like an open switch. Okay? Any question? Okay, a lot of applications. So that here is the setup used by Heinrich Hertz in 1887. So Maxwell worked with his 4 equations, and he predicted that light was an electromagnetic wave. He predicted, just by playing with those 4 equations, he predicted that light is made of an electric field that induce a magnetic field, that will induce a magnetic field, that will induce an electric field, and so forth and so on. So he predicted that, and he predicted the speed of light, but there is no proof. In 1887, Heinrich Hertz made that amazing setup. Like, you have to be a genius to do that. And for the first time, electromagnetic waves were detected, proving that light is a wave, because they were not sure about the nature of light. Okay, so that was the proof. So how did they do that? You see, he used the capacitor. So what's happening here? So they didn't have AC at the time, so he used a mechanical switch. So on, off, open, close, open, close, open, close. So he created an alternating current here, right? And here it's a step up transformer. So he was able to boost the voltage up. And you see here, you have a capacitor. Okay, so 2 electrodes. One will charge positively, the other one will charge negatively. So he's charging the capacitor, but the current cannot flow here because there is a gap. Okay, so you charge this one negatively, you charge this one positively, you are holding the charge. So it's like a parallel plate capacitor, but no charge can flow until you're gonna reach the voltage high enough between those 2 connections, and you're gonna have a spark. And all of a sudden, the current is gonna flow back and forth. You're gonna have resonance, okay? And that will make this electromagnetic wave. So it was the first time, okay? Because current is just electric field shaking. The current is shaking, the magnetic field is shaking, the current is shaking, the magnetic field is shaking. You have an electromagnetic wave, and he detected that with an antenna. That was a big breakthrough. He died very young. It's very sad because, of course, he got the Nobel Prize, I think. After that, it's not clear what happened to him. But he was very young, just after this big breakthrough. And just after that, you have this other genius, Tesla, who died young, penniless also. he came up with the Tesla coil and he built on that. Okay, so he did the same setup but took it a step further. So and this is something you can buy now. It's very cheap, you know. You can buy on Amazon a Tesla coil. It's super cool to play with it, but it's the same idea. Okay, so here you have a transformer, and you're gonna that's your capacitor here. Okay, and you're gonna charge the capacitor until you reach a voltage high enough. Okay, so then the current will make it through the gap, and then you have oscillation in that circuit, and you step up the voltage with a Tesla coil to a very, very high voltage. So this is it's called resonance because you have oscillation in the circuit, but those oscillations you make it go higher and higher and higher. So higher voltage, higher voltage, higher voltage. And he was trying to work on wireless, except it's Marconi who got the Nobel Prize, which was very unfair. But the idea is resonance. You know, you have a boxing bag here and you keep hitting and hit and hit and hit at the right resonance. The bag is going to go higher, 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 higher. Same thing in the Tesla coil. You have resonance and the voltage is going to go higher and higher and higher and higher. And you can look it up how it works, but it's built on that setup, and you have a capacitor and you have an inductor. Yes, Tesla coil. You see, you have your capacitor. Here, the capacitor is going to charge, 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 charge. Ooh, the voltage is so high that the current can flow, jump the gap. It's going to oscillate, oscillate, oscillate. Okay, and here you have a secondary coil, so the voltage will be stepping up. So step up, and you can get very, very, very high voltage. So there is resonance between this circuit here and that circuit there. So this circuit is punching this one. Higher voltage, higher voltage, higher voltage. It's a very simple setup, as you can see. It's not very complex, right? A few lines, but it's genius. Okay, how are you doing? So we're gonna start a new unit, which is magnetism. And with it, so that will be unit 3.1. So with it, you're gonna have another unit here in parallel. Okay, so it's gonna be, no, it's not going to be 3.1, just kidding. 5. It's going to be unit 5. It's called magnetism, but you have another unit called big idea. Okay, and I try to summarize everything in the big idea. It's going to be all the electromagnetism. So we can review for the test. So in that case, you see big idea, positive charge. What's going to happen? The electric field is out or in? Out. Negative charge is going to be in. This is a parallel plate capacitor. The electric field is uniform. The positive charge goes with the line. Between here, you have a voltage drop, which is equals to the electric field times the distance. So it's review. Remember, if I ask you this, if you have a conductor, the voltage will be the same inside on the conductor. Electric field is 0, but not the voltage. If you have 5,000 volts on the surface, it's going to be 5,000 volts inside because the electric field equals 0, so you don't have to do any work when you have a 1 Coulomb charge. Remember that when the conductor is sharp, you're going to have very, very, very strong electric field. Okay? Electric field is the slope of the equipotential. The electric field is always perpendicular. So in red, you have the electric field of a dipole. And in green, these are the equipotential. So the electric field is always perpendicular to the equipotential, and it's going to show you which direction for a positive charge to follow to get down the potential as fast as possible. Okay, so that's a definition of a dipole moment. This is called a Faraday cage. You cannot have a charge inside a conductor. You cannot have an electric field. So except for the noise, you're going to be safe. Definitively, one question about that. When you have like positive or it's a negative, so negative and positive, so you can accelerate an electron through the voltage drop. Okay, so you have potential energy, which is QV equals to the change in kinetic energy. So you have to find the final speed or something like this. Cathode ray tube, negative, positive, the electron will speed up. And that's the old TV screen. Okay, what else? You can use an electric field for linear accelerators. You can make a charged particle go accelerate because there is a force applied to it and crash. Okay, so these are the equations that we have that you need to use. Don't forget, you don't have the same equation. So electric potential is not the same thing as electrostatic energy. Because I checked last time, I'm not sure if in your equation sheet you have both of them. Okay, so you're going to talk about the electrostatic of distribution of charge. So it's going to be K Q1 Q2 over R1 R2 plus K Q2 Q3 over R2 3. So this is called the electrostatic energy of a charge distribution. Not the same thing as the potential, which is at a given point. The potential will be the potential energy of 1 coulomb relative to infinity, but it's at a given point. It's a scalar field. This is the energy of a configuration, like a water molecule. And that's going to be the electric field. It's following an inverse square law. This is Coulomb's law. Okay, and we're going to talk about magnetic field next time. Any question? So I just show you. So this is called the RC circuit. You see, charging, discharging, charging, discharging. That's how it works. So everything happens like you do have current going through. So a capacitor will not stop AC. A capacitor will let go AC. But if you have DC, so if I remove that, are you listening? Don't space out, right? So if you have DC, you see after a while, nothing can go through. So a capacitor will stop DC. So in electronics, it's going to be used to remove a DC component from a signal. So capacitor let go AC but stops DC. That's what? Huh? So yes, I actually they use that for the noise, right? I mean, I had a I don't know where my things gone, but you're right because it's like it attracts AC. So if you have a low pass filters, you have the power supply here, power supply, and you put a capacitor here and you have a load there, and you have a signal with high frequency like and noise, like low frequency and noise, all the high frequency will be dumped through the capacitor there. Everything high frequency will go there, and what will be left here will be the signal. So that's why you get rid of the high frequency signal with a capacitor. So you have low pass filter, high pass filter. So here you are filtering the high frequency, which is the noise, because a capacitor loves AC, but it stops DC. It's somewhere in my slide, except I don't know where it goes. I lost the slides. So anyway, okay, so let's stop here because I don't know